Okay, folks, it's that time, so we are going to go ahead and get started. Today we're going to continue performing combustion. Excuse me. We're going to continue performing stoichiometry. So, in other words, the chemical mathematics associated with reactions. And we're going to perform several of those. Now, I just wanted to give you a heads up of what is coming for the remainder of the semester. So today I am performing the stoichiometric calculations. On Wednesday, I'm going to introduce the concept of molarity, and we're going to perform some calculations of molarity and start getting into molarity, some conversions involving molarity as the conversion factor. And then on Friday, we're going to get into, we're going to continue discussing molarity as a conversion factor and get into dilutions with molarity. And folks, that is going to be the end of new material, because on Monday of next week is your 4th exam. And I plan to not go over any new material on Wednesday. Instead, it's going to be me discussing how to study for my final exam. And then the final would be the following Wednesday. So that just gives you a little bit of a heads up about how things are going to occur for the rest of the semester. Any questions? I will say that I am starting to put in, even though I know I'll have to go in and change some of the numbers, I am starting to put in attendance points and the bonus points that I've got. So that you can see all of the grades. I am also going to be doing a significant push next Monday night to get your exam graded, so that hopefully by Wednesday of next week, I can tell you exactly where you stand with the 4 exams, or whether or not you want, basically help you to make that decision of whether or not you're going to take the final exam. So that is the plan. Any questions? Okay, so how many grams of butane must undergo combustion to produce 2.46 grams of water? According to the reaction where butane reacts with oxygen to form CO2 and water. Okay, let's identify what we have been given. We have been given 2.46 grams of water. And let's identify what we want to solve for. We want grams of butane. So knowing this information, now we're going to break this down and see what we need to do. We have water, we have butane. Because we have 2 different materials, it means we're going to need a mole to mole. And the mole to mole ratio, since we're dealing with the balanced chemical equation, comes from the coefficients of that balanced chemical equation. So there's 2 moles of butane to 10 moles of water. The next thing that is you notice is that we are dealing with grams of water. Anytime you're working with grams, it means you need the molar mass. We have 2 hydrogens at 1.008 each. And we have 1 oxygen at 16.00. So the mass of water is 18.016 grams of water is equal to 1 mole of water. Now, the last thing we note is we need grams of butane. Again, grams indicates we're going to need the molar mass. We have 4 carbons times 12.01 each. We have 10 hydrogens times 1.008. That's 48.04 for the carbon and 1080. I think. 10.080 for the hydrogen, for a total of 58.120. So that's 58.120 grams of C4H10 is equal to 1 mole of C4H10. Now that we have broken down what our possible conversion factors are, we're ready to key this in. So we start out with the 2.46 grams of water that we were given. The very first conversion factor needs grams of water. So that's going to be the second one we developed, where we had 18.016 grams of water is 1 mole of water. The 18.016 grams of water went into the denominator so that the unit and the substance would cancel, leaving me moles of water. Now we're going to use a conversion factor that has moles of water that we haven't already used. So we're going to use the first one. The 10 moles of water will go in the denominator, with the 2 moles of butane in the numerator. We place the 10 moles of water in the denominator so that the unit and the substance would cancel, leaving us butane. And now we need our moles of butane from a conversion factor we haven't used, so we're going to use the third one. The 58.120 grams of butane will go in the numerator, and the 1 mole of butane will go in the denominator. We put the mole of butane in the denominator so that the unit and the substance would cancel, leaving you grams of butane, which is what you were asked to solve for. So 2.46 divided by 18.016 times 2 divided by 10 times 58.120, and you get an answer of 1.59 grams of butane. Questions? Let me give you one to work on. How many grams of sodium sulfate will be formed if you start with 200 grams of sodium hydroxide? According to the reaction, according to that reaction. Okay. So when you take and separate everything out, you would find that you need a mole-to-mole ratio because sodium hydroxide and sodium sulfate are different. And according to the balanced reaction, there's 2 moles of sodium hydroxide to 1 mole of sodium sulfate. You would find you need the molar mass of sodium hydroxide, which when you add it up is going to be 40.07 grams of sodium hydroxide. And you would find that you need the molar mass of sodium sulfate, which comes out to be 142.05 grams of sodium sulfate in a mole of sodium sulfate. You then set up your problem starting with the 200 grams of sodium hydroxide. The first conversion factor had to have grams of sodium hydroxide in it. So we used the molar mass of sodium hydroxide. The gram piece went into the denominator so that the unit and the substance would cancel out on the previous piece, leaving you moles of sodium hydroxide at that point. You would then use your other conversion factor that has sodium hydroxide, which is your mole-to-mole ratio. The 2 moles of sodium hydroxide went into the denominator, while the 1 mole of sodium sulfate went into the numerator. The sodium hydroxide cancels out, leaving sodium sulfate. You then used your molar mass of sodium sulfate to get rid of moles of sodium sulfate by placing it in the denominator and the mass in the numerator. Now, when you perform the math, you get 354.5. Now, folks, your numbers may be a touch different than mine. As previously mentioned, it is dependent upon the periodic table that you have. But it should be right around that 355 mark. Might be slightly higher than 355, slightly lower than 355, but it should be right around the 355 mark. Question. Hopefully conversions are becoming much easier the more we do them, because we've been working on these for quite some time of a variety of types, but the process is always the same. I will tell you on an exam, the balanced chemical equation will be a separate question, meaning you'll be asked one question to balance the reaction, but on this question, I would give you the balanced reaction. You will have a separate question where you would be asked to calculate a molar mass. But on this question, I would give you the molar masses. In other words, I'm not going to have it where you should be starting with the correct information to do the problem. We're doing all the steps here because all of the steps are important, but we're on a test, it's going to be separated out as separate questions. Would you like another problem to do or move forward? Those that want another problem to do, raise your hand. Okay, that's the majority, so we are going to do another problem. theoretical yield, don't let that term burn you. Theoretical yield is grams. It's basically, in theory, how much can be made in grams. So don't let the word theoretical yield throw you. It's still the same math we've been doing. Oh, you do need the equation, though. That's what you're waiting on. There you go. Okay, let's see how it's going. So you would have had 16.5 grams of iron 3 oxide that you started your equation with. Your first conversion factor would have involved iron 3 oxide, specifically the mass, and that was 159.69. Is equal to 1 mole. You would have placed the grams in the denominator to cancel, leaving moles. You would have then used the fact that there's 1 mole of Fe2O3 to 2 moles of Fe in order to convert it in between the two compounds. The moles of Fe2O3 canceling out, leaving moles of Fe, and then you would have converted that into grams of Fe using the fact that 1 mole of Fe is equal to 55.845 grams of Fe. Moles of Fe going in the denominator so that they cancel, and you would have gotten 11.5 grams of Fe. Yeah. Again, your number may vary slightly, but overall it should come out to be the same. So folks, we can develop a flow chart that helps us to navigate these conversions that we've been doing with compounds and with formulas and balanced chemical equations. So if I have atoms, ions, or molecules of A, and it could be atom of A, or ion of A, or molecule of A, you're going to use Avogadro's number to get to moles of A. If you have grams of A, you're going to use your molar mass to get to moles of A. Now, if you're working with two different compounds, that's when you need your mole to mole ratio. If it is, it'll come from the formula. If it is an element within a compound, but It can also come from the coefficients. If it's two substances in a balanced reaction. And then once you get to moles of B, again, you can convert up to atoms of B, ions B, molecules of B using Avogadro's number. Or if you get to moles of B, you can convert it to grams of B using the molar mass of B. So this kind of gives you a flow chart where what is represented on the arrows represents the conversion factor. And what is represented in each location represents what you have at that point. So how can you use this particular process up here? Let's say I gave you moles of one thing and I wanted moles of another thing. Okay, so I start with moles of A. I want moles of B. That means I just need a mole to mole ratio. That's the only thing separating these two. Or let's say I start with grams of A and I want atoms of B. Then the conversion factor I'm going to need is I'm going to need my molar mass. It's going to be the first conversion factor I'm going to need of A. I'm then going to need a mole to mole ratio that goes between A and whatever B is. And then I'm going to need Avogadro's number to get there. So if you're struggling with the method I have been showing to you, where we take our starting quantity and from that deduce what all we need, this is another option for you. It gives you yet another possibility to help you get through it. For me, this is the easiest, but at the same time, because I'm not good at memorizing things, but I can go two different substances, mole to mole, grams, molar mass. I know those things. But if that is not working for you, here is, you can use that flow chart as well. Any questions? I'm going to introduce Wednesday's topic, but we're not going to I'm going to introduce the terminology for Wednesday's topic. We're not actually going to get into the mathematics today. On Wednesday, we are going to start talking about the concentration unit of molarity. Molarity describes a solution. You use concentration terms You may or may not have used molarity, but you've used concentration terms. When you first make tea on the stove, do you want to drink the tea immediately? No. Besides it being hot, why? Why would you not want to drink the tea you just made on the stove immediately? Yeah, you're brewing it, but why? Why would you not want to drink the brewed tea immediately? Most of the time you make it strong. Then you pour it up into a jug and you add water and you're diluting it. So if you've ever used the terms, well, that's stout, that's strong, to describe a taste of a liquid, you're using a term of concentration, but it's a very vague term because your idea of stout and my idea of stout are two different things, possibly. I mean, it's kind of like coffee. A person's idea of stout is two different things when it comes to coffee for the most part. So you've used these terms, but they're very vague. Molarity cuts through the vagueness. It describes exactly how much is in there. So it describes a solution. Now there are two parts to a solution. There is the solute and there is the solvent. The solute is sometimes described as the minor component. It is also described as the component that changes state of matter. The solvent is the major component in a solution. And together, again, they make the solution. Now, when we're using molarity, molarity is represented with a capital M, and it has a formula. The formula for molarity is that it is moles of solute divided by liters of solution. And it is this term that we are going to learn to calculate with. We're going to learn how to calculate it. We're going to learn how to use it as a conversion factor. And finally, we're going to talk about dilutions, and I will pick that up on Wednesday.